Hello and welcome to PCMINR.com, and in this video you're going to learn about Carnot Engine by Sonal Gupta. So what is a Carnot engine? See, it is just a simple heat engine, or we can say a device which converts the heat energy into mechanical work, and it is based on the second law of thermodynamics, according to which there is no machine that can convert all the heat energy into work without rejecting any heat to the surroundings or without any heat losses. So this Carnot engine, it was developed by a scientist called by the name of Sadi Carnot. He devised an ideal cycle of operation for a heat engine, and this Carnot engine is actually an ideal heat engine. So we are not talking about a real engine which we see in our daily life. So this was designed under the specific conditions. So it is based on 4 cycles, as you've already learned in thermodynamics about isothermal expansion, isothermal compression, adiabatic expansion and adiabatic compression. So this Carnot engine is going to work on the basis of these 4 cycles. So it is going to go through all these 4 steps or a complete cycle. And essentially the main construction thing would include, so here are the essential parts of an ideal heat engine. This is one, you need a source at temperature T1. This is at a high temperature, and it's in fact at such a high temperature, and we say it has infinite thermal capacity, that whatever amount of heat is drawn by a working substance, it doesn't matter to this source. Its temperature will not vary, right? So it's like a sea. If you take a bucket out of it, 10 buckets of water out of sea, it's not going to impact the sea. So we have a source at temperature T1 which is having an infinite thermal capacity. So any amount of heat can be drawn from this without changing its temperature. The next important thing is the sink of heat, because this one, that is sink of, we call it as sink, and it's at a temperature T2. This is at a low temperature. So this is something we maintain at low temperature so that any amount of heat can be rejected to it, because this working substance, when it is going to work, absorb this heat and do some work and reject the amount of heat, it has to be given to something, and that is our sink. So sink absorbs or takes in all the heat rejected. So it should be at a very low temperature and also of infinite thermal capacity so that it can absorb any amount of heat. So both of them are of infinite thermal capacity, so that any amount of heat drawn from the source should not impact it, and any amount of heat rejected to the sink should not impact the sink. The third important part of your ideal Carnot engine is the working substance. So working substance here is your ideal gas we have taken, a gas which we take inside a cylinder. Now if you look at it carefully, there are 2 important things to be noted about this cylinder, that the base of the cylinder is perfectly conducting. Why it has to be conducting? So that when I place it on the source or on the sink, it should be able to absorb the heat or reject the heat, and that is possible only if the base is conducting. But the sides, rest of the thing or the entire cylinder is insulated completely, so that there is no heat loss to the surroundings. Right, so these are the essential parts. So I would just write them down. The first important part is your source. We call it as a source of heat, and it is maintained at a temperature T1. Second important part is a sink. So something has to act as a sink, so that is maintained at a temperature T2, and of course your T1 is greater than T2 with infinite thermal capacities, both of them. And third one is a working substance, and your working substance is an ideal gas. So we can write that down. Right, so these are the essential parts. So we have defined the Carnot engine and we have written all the essential parts. For this, you just need to draw this clear diagram, a labeled diagram, and just write these things. That should be sufficient to explain for the examiner. Now we come to the theory part, or how the Carnot engine is going to work. So the first step includes isothermal expansion. For isothermal expansion, the gas is allowed to expand slowly. As you know that for isothermal expansion, it is important that the gas should expand slowly so that it gets enough time to lose the heat to the surroundings. So now when it is expanding slowly, a part of heat which has been absorbed from the source is used up in expansion. That work is being done on the gas by the gas, and rest is lost to the surroundings. So the temperature of the gas remains constant because isothermal means the temperature should not change. That means what we are going to do is that the cylinder which is containing the gas is first placed on the source. Now when it has been placed on the source, as we saw in the last figure, so this ideal working substance is placed here first on the source. Now at this time it absorbs the requisite amount of heat from the source because its base is perfectly conducting. Now this because of this the temperature would rise, but we don't allow the temperature to rise because the operation here happening is isothermal expansion, so we can't allow the temperature to increase. So that is why the expansion is happening slowly, and the amount of heat energy is absorbed is we would take it as Q1 as the amount of heat energy absorbed, right? That is the heat energy absorbed, and W1 would be the work done by the working substance in expansion, right? So work has been done and the rest of the heat would be lost to the surroundings. So the gas is expanding isothermally, so T1 remains T1 only. So isothermal expansion is happening here. Now for that, what is the work done? How can we calculate it? You've already done this work done calculation in isothermal expansions. That is equal to W1, heat energy supplied, and the work done. It's equal to PdV because there is a rise in volume happening here because the gas is expanding. So if we take it upon for a small amount of volume dV, then for the entire volume expansion from V1 to V2, you will get the work done as integral of PdV. And because we know that PV is RT, so P can be written as RT upon V dV, and the integral would happen where RT would go out because they are both constants, and the temperature in this case is T1, and the integral of 1 by V is log of V. So that's going to be log of V within the limits V1 to V2. So ideally it gives me RT1 log of V2 minus log of V1, and which I will write as log of V2 upon V1. Now that's my first equation I got, the work done in isothermal expansion. And this work done, which we have derived here mathematically to be RT1 log of V2 by V1, we can also express it in terms of the area under the curve of isothermal expansion. So let me show you that. So this is the work done here if we talk in terms of the area under the curve. So if we look at this curve for isothermal expansion is going from A to B. So A, B, M, K, A, whatever is the area under this curve, that will give us the work done. So that Q1 which we calculated as RT1 log of V2 by V1 is equal to the area under this curve. So we can write down that W1 is equal to area of A, B, M, K, A. That's equation number 1. Now let's go to adiabatic expansion. Now this working substance is picked up and kept back on the insulated stand. Now when it is kept on the insulated stand and it has been removed from the source of heat, and we have kept it on an insulated stand, means it's completely isolated from the surroundings. So now all that heat absorbed is used in further expanding from the volume V2. We had already reached this pressure and volume V2 P2, and now it's further changing it to C, that is V3 P3, and because here the gas is thermally insulated, so no heat exchange is happening in the surroundings. So whatever temperature was there, it will fall down because of the expansion, and the expansion of the gas happening would lead to what? The expansion would lead to a fall of temperature. So now it's no more an isothermal expansion happening. The fall of temperature happens to T2. Now the temperature falls to T2. So therefore, this time we have the adiabatic expansion going on when the heat exchange with the surroundings is not allowed. So whatever heat it had absorbed all went in the expansion, and further it kept on expanding, so the temperature fell down further. So the work done this time, W2, is again the integral of PdV, because still there is a change in volume happening from V2 to V3, and this time we get it as R times T2 minus T1 and upon 1 minus gamma. So that's an expression which we have already derived during adiabatic expansion. So this is equal to, if we talk in terms of the area, then we get it as, so it is going to be area only under this curve. This is the adiabatic expansion happening. So this curve, this area. So W2, the work done during adiabatic expansion, is going to be, for the adiabatic expansion, it will be area under the curve BCNMB. So that is our equation number 2. So 2 works we have calculated. Now we are going to talk about isothermal compression. Now in the third step, this cylinder is again picked up and kept on now the sink at temperature T2. So now the cylinder, when it is removed from that insulating pad and kept on the sink, the piston is moved down slowly. So this piston is moved down so that the gas is compressed. So when the piston is moved down and the gas is compressed slowly, what is going to happen? Just the reverse of the first case. So when the slow compression happens, that is, a piston is compressed slowly, the gas is compressed, the volume and pressure would change, of course. So now we get it from P3 V3, the situation, the parameters change to P4 V4, and this time again, because it's all retained, the heat can be lost to the surroundings. So when we are compressing the gas, it is increasing the temperature of the gas. So whatever amount of heat is being absorbed or supplied during the compression, right? The compression, you would say, raises the temperature, but the compression which raises the temperature, we have placed the cylinder on the source, so it is going to reject the heat to the source so that the temperature again remains constant. So heat is allowed to be rejected, right? The heat is allowed to be rejected to the source, to the sink. Now this time again the temperature remains constant. We can write here, therefore the temperature T2 remains constant. So no change in temperature is happening. So what would be our work done? So work done, which is of course based on the amount of heat energy. If we say Q2, sorry, this is Q2, when we say this is the amount of heat rejected to the sink, the amount of work done on the gas is based on that. So whatever amount of work is done on the gas, it is lost as heat to the surroundings. So Q2 is equal to W3, and that is now the integral of negative of PdV. Negative because the work is done in compressing the gas. So we are doing it from volume V3 to V4, and we again get it as RT, but this time with all with the negative sign. So RT2 log of V4 by V3, following the same steps of integration. And if we talk in terms of the area under the curve, then it's going to be, so in terms of area, it is going to be the area under this curve, C, D, L, N, C. So this entire area would be expressing the work done. So we'll write it down here, that this work done during isothermal compression is equal to the area under the curve C, D, L, and C, and we put a negative sign here because it's the compression happening. Now the cylinder is picked back from the sink and again kept on the insulated pad. Now this time further it is compressed the piston is further moved down so that the compression continues, but now it's completely insulated from the surroundings. So that is why we are saying the adiabatic compression is happening. So no heat loss would occur here. Now, since no heat loss occurs during adiabatic compression, that means whatever amount of heat is being given it during compression will raise its temperature. Therefore, the temperature of the gas would rise back to T1. When it has fallen from T1 to T2, now it would rise back to T1 because of the compression, and there is no heat exchange happening, so it can't even lose that heat. So whatever amount of heat is supplied, it is being used up in rising the temperature. So work done this time W4, while adiabatic compression going on would again be PDV but with a negative sign. Volume you're changing from V4 back to V1 because we compressed it, and it's again minus R times T2 minus T1 upon 1 minus gamma. And if we want to look at it in terms of the area under the curve, we would find, so it's going to be the area under the curve DAKLD, that means this area. So we'll write it as negative of area DAKLD. So we have also expressed all the work done in terms of the area under the curve. Now we have already calculated all the find out all the four equations. So we would find out what is the work done by the engine per cycle. So this was cycle 1, where in the first case we have total work done by the gas, right? So when the work is done by the gas, what do we get? The total work is equal to W1 plus W2, because by the gas during expansion, when gas is expanding, the work is done by the gas. So W1 plus W2, and work done on the gas would be in the last two steps when it is compressing. So work done on the gas is during compression because we are doing work on the gas. So that would be W3 plus W4. So what is the net work done? Therefore, net work done per cycle would be the sum of all of them, out of which of course 2 are positive and 2 are negative. So we would write W1 plus W2, and out of that we subtract W3 plus W4. And since my W2 and W4, they are equal in magnitude, if not about sign, if you just talk of the magnitude, so they would cancel out, and hence my net work done is equal to W1 minus W3, and W1 was Q1 minus Q2. So we simply arrive at the equation that W is equal to Q1 minus Q2. So in Carnot heat engine, the net work done by the gas is numerically equal to the difference in the two heats absorbed and released, or we can say the area of the loop. So entire area just within this loop will represent the work done, right? Nothing outside it. So amount of heat absorbed definitely is greater, and out of that if we just subtract the rejected amount of heat, so whatever was the extra heat has been used up in doing the work. So the net work done by an ideal Carnot engine is equal to Q1 minus Q2. Now if we talk about the efficiency is always output upon input. So that would be output is equal to Q1 minus Q2, the work done, upon Q1, the heat energy absorbed. So that would be 1 minus Q2 upon Q1. That is in terms of the ratios, and we can further also write it as, because the temperatures and the heats will be directly proportional, so I can also write as 1 minus T2 upon T1. So my efficiency, as you can see from this equation, it can never be 100%. Therefore, efficiency can't be 100% because there is some subtraction happening here. If the Q2 and Q1 are equal, right, then they would cancel out and I would get the efficiency to be 100%. So efficiency depends on the source of, from this equation we can say that the efficiency of a Carnot engine depends on the temperature of the source T1 and also the temperature of the sink. It does not at all depend on the nature of the working substance. So efficiency depends on the temperature of the source T1 and temperature of the sink T2, but it is independent of the working substance or of the nature of the working substance. So I hope you understood the complete working of a Carnot engine in terms of its 4 steps which it goes through in every cycle. If you find the video helpful, please like us, subscribe us and follow us on Instagram and Facebook at PCMINR.com. Thank you for watching.